Now we're going to talk about operators for problem solving. So what are the available options for us when working on a problem? You might think it's something simple like putting on your clothes, but most people talk about operators as more up here, sort of top-down rules we used to apply. Okay. So algorithms are a set of procedures, we've actually talked about these before, to solve a given set of problems which always produces an answer. So if you're trying to find what to wear for the day, you can try your closet, you can try the bathroom, you can try the kitchen floor, wherever you normally leave them. But the more traditional problem version of this is the Lucan's water jug problem. So what they do is they give people a set of jugs that hold a certain amount of water. So jug A holds 15, jug B holds 39, and jug C holds 3. I need 8 gallons. And so what you'd say is I need 1A and 1C, pour all that into B, so you have 18 in a 39-gallon jug. Okay, so that's Lucan's water jug problem. What they do is they get you stuck solving the problem in one particular way, and then they mix it up on you and see how well you do. The problem with using algorithms as a problem-solving heuristic operator is that they're really slow. While they will produce the correct answer every single time, they tend to be very tedious. And remember, we don't like to think very hard. So what do we do instead? Instead, we use heuristics. Heuristics are rules of thumb that usually produce a right answer, but not always. So algorithms always give us the right answer. Heuristics often give us the right answer. Couple types of heuristics. So there's a random search heuristic, hill climbing, and Meansends Analysis. So the one that's sort of the easiest is a random search tree, where we generate an idea and test if it works. So it's trial and error. I'm going to pick a move. Did that work? Nope. I'm going to try this move. Did that work? Nope. I'm going to try that move. Did it work? Nope. Until you get to the goal state you're looking for. That is also very slow, so we tend to use more top-down sort of rules based on what is going on in the problem, such as hill climbing. And what we'll do is we'll look one move ahead and choose the move that gets us closest to that goal. So if you're trying to climb a hill, you're looking right ahead and moving towards the top of the hill, which is the goal state. The problem with hill climbing is that you can go terribly wrong. So if I give you the problem, this is worded in a bunch of different ways, and pretend that the fox, rabbit, and carrot are magic. And so I have a fox, a rabbit, and a carrot on one side of the stream, and I have to get them all across the river in my magic boat. The boat can only hold 2 things at once, but you can't put 2 things that will eat each other in the boat at the same time. And the boat is not totally magic, it still needs somebody to steer, even if it's the magic carrot. So what you do is people will say, well, I can't put the fox and the rabbit together, and I can't put the rabbit and the carrot together, so clearly I have to start with the fox and the carrot. So I'm going to float them across the river. So I've got the rabbit on one side and the fox and the carrot on the other, and now what do? Well, I could send the fox back, but then I gotta do something with that rabbit. So I can send the rabbit over here, but then I gotta do something with that carrot. So I'm gonna send the carrot over here, and then now I'm good to have the fox and the magic carrot coming back. And so hill climbing, what'll happen is people will get stuck in one of those moves because it moves them away from their goal. So people don't like to do the thing where you have to send an item back because it gets them further away from their goal. And that's called backup avoidance. We don't like to undo things that we've previously done. So if you're working on an assignment, you realize that you've misunderstood the rules, people don't like to start over, essentially. So you can see that in the Tower of Hanoi problem and that fox problem I just showed you, especially in children. The Meansends Analysis is probably the best type of heuristic, where a problem is broken into little mini sub-problems. And this is often looked at in a verbal protocol analysis, where you ask people, okay, I'm going to get you to solve this problem, talk aloud while you solve it. So we haven't really talked about protocol analysis from Chapter 1 very much because it isn't used too often. This is a perfect time to use it. So we can look at how people are working their way through the problem by getting them to talk out loud. Means-ends analysis is more complex, but people tend to like it. So college is a giant means-ends analysis. Sub-goal number 1, gen eds. Oh, sub-goal number 2, my major requirements. So if you've done any kind of degree audit, you've looked at a means-ends analysis. Lastly, what we can do is build a computer, this is artificial intelligence, to act as if they're human and compare how human solves the problem to how computers solve the problem. It turns out that computers are way more efficient than we are, and so looking at how can we program computers to act like us. So one neat thing is they've tried a means-ends analysis with to the Tower of Hanoi with sub-goals in an MRI machine. And unsurprisingly, that prefrontal cortex that sort of does everything was involved with the steps that require backing up. So moving the pieces backwards from where your goal state is. People who have damage to the prefrontal cortex have a very hard time solving problems that require backing up. So there's something about the prefrontal cortex, it might be the attention or the working memory component that is necessary for backup problems in problem solving. Another neat thing with brain activation in problem solving, if you are looking at how many sub-goals people have activated in a means-ends analysis, you will find that the more sub-goals they have, the more brain activation you get. Okay, so there's more activation of the prefrontal cortex. And as those sub-goals get solved and you get closer and closer to the problem, you get less activation in the prefrontal cortex. So what happens is your brain is solving the problem and it doesn't really, sometimes it doesn't tell you, and you get less and less activation until the problem is solved and then no more activation. Last type of operator we're going to cover is analogies. Algorithms, heuristics, analogies. We're terrible at analogies. It's bad. So analogical reasoning, rather than starting from scratch, you think of a similar problem and try and adapt that to the current problem. So I do this when I work on computer code that I'm not quite familiar with. I'll take someone else's code and try and modify it to make it work for what I'm trying to do. And that's an analogy. So it's a process of comparison from the source domain, and we didn't talk about the bicycle thief situation, but applying it to another domain. So bicycle thieves, people who steal, who are trying to solve the combinations on locks on bicycles, and try and apply that to finding someone's password on a computer. So thinking about analogical reasoning, one of the most famous cases was Niels Bohr, and he basically explained the way that hydrogen atoms work by thinking about the solar system. So I'm going to apply this the way the solar system sort of rotates to hydrogen atoms. But that analogy was so strong that it really helped people understand atoms. They teach us to you in basic chemistry class. Another famous example is with emotion research, applying a temperature rule to that. So as emotions get heated, you're applying as things get hot, or if you feel really cold, then you are emotionally drained. So applying that to understanding emotions. So there are several parts to analogy. First thing you have to do is retrieve the similar problem from long-term memory and compare that to the problem that is holding in working memory. So I'm retrieving the information I had before, and I'm holding on to the things in working memory. Mapping is when I overlap them. So do the two problems match enough for me to use it? But that decision is considered evaluation, so mapping is just sort of overlaying them. And that's the general 3 rules. The next steps that you take are more expertise-based, but abstraction is isolating the pieces that actually match, that are useful to you. And prediction is when you say, well, if I apply this rule, this is what's going to happen next. Okay, so the first 3 are super important. We do that all the time. The next 2 are more complex rules that we'll use if we're trying to do this a lot. So here's a famous example. It's called the military problem and the doctor problem. So they give people this this example of a small country who has a dictator. It's in the middle of the country, surrounded by farms. There are lots of roads, and we're going to capture this fortress. If I take my entire army across these roads, we're going to blow up because the dictator is mean and he's placed mines on the roads such that small bodies can pass over, since we still need to get people in and out, but large bodies are going to blow up. So what do? This problem is usually solvable. People say, well, you surround the place because it's small. You lead lots of troops in from different directions and surround the fortress. What they do then is they give you this problem. So you are a doctor with a patient who has a tumor in their stomach. It's impossible to operate, but you've gotta. Otherwise, the person's going to die. So I have a laser that can destroy the tumor, but it has to be a high intensity. Unfortunately, at that intensity, it kills a lot of other things too. And so at lower intensity, it's harmless. So what do? Well, the solution to this problem is sort of the Ghostbusters solution. Cross the beams! Okay. But what's going on is the solution to both problems are precisely the same. Bring in lots of people from lots of different directions. People don't see that they're the same. And so we're actually quite terrible in analogies because we won't notice the relationship between problems. So we can't see that the solution for this one is the same solution for this other one. So not very many people will solve the doctor half. Most people solve the military half, but not the doctor half. So you have to be explicitly told, hey, why don't you use this problem to solve it that you've already worked on? And then even then you're still going to have trouble, because what we'll try to do is use the superficial surface facts. So this is a very novice approach. These two problems don't look the same, but I can try, and you just can't make them match. So analogy is actually rather difficult for people because of these problems. So I'm going to talk about the Raven's progressive matrices. I'm going to give you some examples. And what it does is it's a convergent task. So it shows us that the prefrontal cortex is the area of the brain that is used when doing analogies as well as Meansends Analysis. And so to bring this back to the brain chapter, kids are not very good at analogy. I mean, people in general aren't, but children are really bad at analogies because that prefrontal cortex is one of the last areas to develop. So myelination, remember, is the greasing of the brain. It starts in the occipital lobe and works its way forward. So the frontal lobe is actually the last piece that gets it. So that's why children are especially bad at problem-solving tasks for a while. So the way the Ravens works is you are trying to figure out what goes here in this bit here. So there is a pattern that goes across and a pattern that goes down. And you were trying to figure out what completes the pattern going both across and down. Okay. In this particular one, we need 3 lines. So that automatically rolls these out. Boop, boop. Wow, that one has 3. Okay. We've got right leaning, left leaning up. So I've got left leaning up. I need a right leaning one, so that's actually narrowed it down enough so I can know that it's a 5. But there are even more rules about how the pattern is rotating, about how the figures are rotating, and then we have a circle, a diamond, and a square. So there are lots of rules that people use to figure out what goes in this last slot. Okay, so some more examples. In this particular one, oops, let's try this again. The line piece is moving down in all of them. So it's got to be one of the low pieces. So not that one, not that one, or that one, or that, any of those. So I'm left with 1 and 3. And as I go down, I am getting more the left and right sides. So it has to be 1 because I need both left and right. Otherwise 3 is a match for this one. That doesn't work. And even better, the pieces, mirrored pieces here are getting closer as they go in. So take a second to try and solve this one. The answer for this one is 4, because we are slowly reducing the number of pieces going across and down. So after we take off all of our pieces here, we're left with only the one in the middle for 4. This is one of the last problems on the Raven's matrices and is one of the most difficult if people actually make it this far. So the answer is 3. And what you're doing is your dotted line here, 2 dotted lines. Okay. So we're adding dotted lines as we go across. So we've got right, left, both, right, left, both, right, left, now I need both. It's number 3. We're also subtracting the solid lines. Left, right, neither, left, right, neither, left, right, neither. So it's number 3. Right. So that really ends the types of operators, so analogies, heuristics, and algorithms. And now we're going to get into something fun. This isn't really in your book, but is problem representation issues. So if you're trying to solve a problem in, let's say you're using problem space theory, you have to really know what to represent in the brain. So how are you dealing with that information, and what if you get stuck? Getting stuck is the interesting part. So this is the mutilated checkerboard problem. And so what they tell you to do is you have a checkerboard, so it has 64 squares, and we're going to take away 2 of them. So I've got 62 squares. I've got these dominoes here. If I have 31 dominoes, can I cover every square on the board with those 31 dominoes? So I have 62 squares, 31 dominoes. Each domino covers 2 squares. So most people say yes because duh, math. But if you're watching this lecture, clearly you know it's no. Well, why not? Okay. So it can't be solved. And so you have to cover 1 black and 1 red square, or blue and white from the other sides, but you can't just cover any 2 squares. And so when you remove, let me go back here, these 2 squares on the outside, you're removing the same color of each one. So let's say those are the red squares. So now I have 30 of one type and 32 of another, which means I need 32 dominoes and not 31. So if I had 30 and 30, I could do it, or if I had 31 and 31, I could do it, but I don't. I have 32 and 30. So I'm not representing the problem correctly. This is Runker's candle box problem. So what they did was they put people in a room with a box of matches, some tacks, and some candles, and said, I need you to light this candle and get it hanging on the wall in some form. So people try to light one end of the candle and like stick it to the wall with the wax. People try to stick the tack through the candle or through the wick, but that doesn't work once you light it. And they have all sorts of trouble with this problem. But the solution is actually really simple. It's like to treat the box as a shelf. And so this is a non-traditional use for this for the matchbox. The two-string problem is also really famous. So I have two strings hanging from the ceiling, and you have to tie them together because this is Magic Land where things have to happen this way. But they're so far apart, I can't grab one and grab the other and tie them. And all you have in the room with you is a chair and a pair of pliers that just look like they're thrown on the floor. So what do? Well, so here's an example of the problem. What you do is you take those silly pliers, attach them to the rope you aren't holding, and swing it like a pendulum. And then go grab the other one and grab it as it's swinging. So people try everything. They stand on the chair. They don't even realize that's what the pliers are for. They use the pliers as grippers. That doesn't work either. All of that is called functional fixedness. It's the tendency to see objects where they can only do what they're normally, conventionally considered to do. So you can only use a hammer as a hammer. But let me tell you, Magalites make really great hammers because they're so heavy. So you can't see a way to use an object for a novel function. So functional fixedness. Another problem is called set effects. This happens to us every day. We solve a problem with the same solution over and over and over again. So this is the Lucan's water jug problem. And if you use the same solution over and over again, you get stuck. And you can't think of a new solution to the problem because the operators are so well learned. There's a lot of interference. Okay? You can't get out of it. Okay. So let me give you a funny example. If you give this to children, they get it like this. If you give it to adults, especially academics, they don't get it so much. Okay. So what's greater than God, more evil than the devil, the poor have it, the rich want it, and if you eat it, you'll die. So even if you aren't religious, you can get it from the last three lines, and the answer is nothing. And so people will get stuck because they're focusing on one piece of it over another, so it's one of those word riddles, kind of problem-solving problems. But in general, it sort of highlights one thing we're particularly poor at, which is focusing on the surface features of a problem rather than the larger story, and that's what makes our operator so bad. And I don't really want to end on a we're terrible, because that's what attention sort of ended on. We're actually very good at problem solving because you got up and ate breakfast or whatever time that you're watching this. You've made it through your day, so we're good at general sorts of problems. But what we do in psychology is we tend to study when things don't work so well, which helps outline when things work well. So people are good at algorithms and they're good at heuristics, but we focus on, okay, well, when can we break this to see what the limits to the system are, especially for problem solving, and then the next two sections, reasoning and decision making.